Okay, this one first. Okay, Assalamualaikum warahmatullahi taala wabarakatuh, and hi everyone. So today we will be talking about the introduction to chapter 4, or the important part in chapter 4. But before we go, we're going to discuss on that particular chapter. So let's recap what we have done on chapter 3. So for chapter 3, is basically we were talking about the force vibration system, single degree of freedom, exciting by harmonic force. Okay, so in chapter 3, the application of force vibration, there are two applications of force vibration that we were talking about. Number one is the base motion, and the number two is the rotating unbalance. Okay, all right, so let's go one by one. So at the beginning, for force vibration, we derive the equation of motion for force vibration. Okay, so we get the mathematical representation of the systems in the form of we call it as equation of motion. All right, so in that equation we have two parts. One is on the left hand side, which is we have the mechanical elements forces, and the other one is on the right hand side, which we have the excitation force. So both force, on the right hand side we have the force which we represent it in the form of harmonic motion, either in sine wave or in cosine wave. Okay, and then when we derive further, we get the expression for magnification factor. We call it as magnification factor, where that magnification factor is a representation of the response of the amplitude ratio in between the steady state amplitude with the static deflection, or with the amplitude at static condition. Okay, which is we represent it as x divided by delta. All right, so delta we get it from F divided by K, and then we get the expression in terms of MCK, or in terms of omega and R. All right, so we can write the equation in terms of 1 divided by K minus M omega, 1 divided by 1 minus R square plus 2 zeta R square, and then square root everything on the denominator part, or we can represent it as F divided by K minus M omega square plus C omega square, and then square root everything. Okay, so we can represent it differently for magnification factor, for the steady state amplitude, or we can represent it differently for magnification factor. And then bear in mind, for force vibration, we have two types of response. Number one, we call it as homogeneous response. Number two, we call it as steady state response, or certain book call it as complementary response plus particular response. It's similar, it's just a mathematical representation. Okay. All right. So for undamped case, zeta is equal to 0, we will have both response. We will have the complementary part, we will have the particular part. Okay, because for undamped case, for free vibration, the amplitude will not be diminished with time. All right, the amplitude is always there. All right, and the amplitude for steady state also will always there. So we will include both response from particular and from complementary as our total response. That is for undamped, right? But for damped systems, we are not really interested to know about the complementary part or from the homogeneous part, because the complementary or homogeneous part, the amplitude will be diminished with time after certain time. Okay, so we are not really interested to know about that one, but we are interested to know about the particular part, about the steady state part. Okay, so that's why in many books, especially our reference book, for damped case, they are really focusing on the particular part, on the steady state part. It is not that the complementary part does not exist, but the understanding or the response is not really important because it will be diminished due to the existence of damping, right? So that is why for damped case, we discuss more on the steady state part, but for undamped case, we discuss both complementary and particular, or we call it as homogeneous and steady state. All right. So in undamped case, I derived it clearly for both response, and then I put it in my e-notes, the expression for the total response. And then on the steady state part, in the steady state part, there is no phase angle. I represent it as no phase angle. Why? Because for undamped case, you just deal with 3 cases of phase angle. One, phase angle is equal to 0. The second one, phase angle is equal to 180 degree. And the third one, phase angle is equal to 90 degree. That is for undamped. Okay, so you have 2 cases, which is 0 and 180 degree, which is one is in phase. We call it as in phase, means that the response is in phase with the excitation force. And the second one, we call it as out of phase, which is the response is 180 degree out of phase with the excitation force. And the third one, we have the angle is 90 degree. That is the resonant case. Okay, the resonant case, right? So that's all for undamped. But for damped systems, we have the expression for phase angle. So look at my e-note, look at my derivation in the other video. So you can see that there is a phase angle in between the excitation force and also the response of the systems. Okay, so please look at that derivation. Yeah. Okay, and then we deal with the magnification factor, and then I discuss thoroughly on the plot that representing the magnification factor. Okay. Where is the K region, where is the C region, where is the M region, how to control the magnification factor and how to lower the magnification factor at every region. Okay, all right. And then we talk about the base motion. After that, after we finish with the magnification factor and the plot and so on, we talk about the base motion. Okay, where we have the input excitation from the base. Okay. This case normally occur in the real industry application, or when you drive your car along a rough surface, or when you have a machine lies on the resilient support and so on. So you have that particular case. So if you have a base motion exciting the machine or exciting the driver inside the car, so that is the application for force vibration. So base motion basically we represent it as displacement excitation. So in terms of displacement, so we can represent that displacement in terms of amplitude of the displacement and the frequency of the excitation. So normally we represent it as y sine omega t and so on, right? So from that we derive, okay, so from that we derive the equation for base motion, and then we get the other expression on the right hand side, which is in terms of y, in terms of base excitation. And then in my e-note, clearly I rearranged it and then I represent it as similar as the normal force vibration. And then we represent the steady state response for that equation, for the base motion equation. And then from there, we get the ratio in between x divided by y. What is x? X is the response of the systems. Y is the excitation from the base motion. Okay, we get the amplitude ratio in terms of, we call it as the displacement transmissibility, TD, and then we represent as a big function on the right hand side, which is 1 plus 2 zeta r squared divided by 1 minus r squared plus 2 zeta r squared, and then everything's to the power of 1 over 2, which is square root everything. Okay, so we get the displacement transmissibility. Okay, so from there we also can derive the phase angle, phase angle in between the base excitation and the response of the systems. Okay, all right. So from this expression, I derive again for force transmissibility. Force transmissibility is basically if we have a machine running with certain forces, and then that force from the machine transmitted to the foundation or to the support. So we try to avoid this one from occurring, all right, especially in the real life. So we derived it again, and then we get the force transmissibility. We represent it as Ft, and I represent it as non-dimensional form Ft divided by Ky as r squared multiplied by Td. All right. So if let's say you want to calculate the force transmissibility, you just multiply r squared Ky by Td, you get Ft. Okay. And then these two expressions is basically arrived from different different physical application, but mathematically it can be represented as similar. So x over y is basically is equal to Ft divided by F. Okay. Force the reaction force to the base. So that F, reaction force to the base, is coming from or coming through the spring element and damping element, right? So these two understanding, normally in the industry, they used it to design an isolator. Especially, you have two isolator, yeah? One isolator for force isolation, and the second one is the displacement isolation. So force isolation is basically coming from the force transmissibility derivation, and displacement isolation coming from the displacement transmissibility derivation. Okay, so then in the latest video, you can see the plot for transmissibility. Okay, you can see there is a crisscrossing area, one region with a crisscrossing area, and you should determine what is the value of R at that particular condition. And then on the right hand side of that region, we call it the isolation region. On the left hand side of that region, we call it as the transmissibility region. Okay, so let me share with you the plot. Let me share with you the plot. So this is the plot. This is the plot. So on this region, that is the the isolator region, and on this region, this is the transmissibility region. So what we try to determine here, we try to get the lower as possible the transmissibility from the system. Because, for example, if let's say you have the base excitation Y as for example 5, okay, 5 millimeter, and you have a response of the system as 6, means that your transmissibility is 6 divided by 5, which is more than 1. That is not good, because with a small number or small amplitude of excitation, you amplify more. So what we try to get here is, we try to get as lower as possible TD. Okay, but be careful, at these two region, these two region, if you this region on the right hand side, if you increase the damping, you increase TD. But on the left hand side here, if you increase the damping, you decrease the TD. So be careful when designing the systems. Okay, so that is the TD. Okay, so we have another one, that is the non-dimensional form representation of the TD. So look at my video, I explained this one before. And then I have another one, the application for force vibration, which is the rotating anvil. I uploaded this e-notes in the future. Then please look at it. Okay, but I will upload the video by this week about this one. Okay, to explain it further lah. All right. So this exam question, I discussed it with the other class. I will upload the video inside the future. Please look at it. Right. So I think that's all for chapter 3. Okay. And today we will be talking about chapter 4, which is chapter 4 is basically multiple degree of freedom systems. What does it mean by multiple degree of freedom system? So I've discussed it thoroughly with you. What is degree of freedom? It's basically if you require one coordinate system to represent the geometrical position of the system, then that is, if you require more than one, that is multiple degree of freedom system. But in our course, we will discuss more on 2 degree of freedom system until the response of the system. So let's look at the objective. Let's look at the objective here. So in this chapter, we will discuss, or we will formulate the equation of motion for 2 degree of freedom systems. You should have, for 2 degree of freedom system, you should have 2 equation of motion. If you are talking about 3 degree of freedom system, you should have 3 degree of freedom system, and so on. All right, and from the equation, you should be able to represent it in matrices here, and then we define the mass matrix, the damping matrix, and the stiffness matrix. All right, from there, we derive the eigenvalue and eigenvector, or normally we call it as natural frequency, and we call it as mode shape. All right, and then from there, we will determine the response of the system. And bear in mind, what we are doing for this particular chapter, we are dealing with free vibration only. We are not talking about the force vibration for multiple degree of freedom system. That is on the other courses, the advanced for advanced vibration. Okay, so that is the idea behind it. So multiple degree of freedom systems, we are talking about 2 degree of freedom system thoroughly. But for more than that, I just introduce you the understanding behind it, okay, the fundamental behind it. Okay, so we will go up to response for 2 degree of freedom system. Okay, so let me check whether you have any question or not. Let me check. Okay, all right, so there's no question. If you have question, just stop me anytime, no problem. If you have question, okay, so since we have 28 here, let me take the attendant. So you should have the attendant now. Okay, so okay, this one is 28. Okay, so I got the attendance already. So if no more questions, so let's discuss this one. So this one is multiple degree of freedom system. Okay, so let's say we have a two block M1 and M2, yeah, moving with coordinate x1 and x2 as presented in this figure. All right, so we have two spring elements, which is we represented as K1 and K2 at the beginning, and then we represented the damping element as C1 and C2. Right, later on we will substitute as K and C. All right, so now in order for us to derive the equation of motion for two degree of freedom systems, first we need to draw free body diagram. All right. So I draw it early on, so easy for us to discuss. So again, in order for us to draw free body diagram for this case here, so we need to make an assumption. Yeah. So both block M1 and M2 moving to the right. Okay, moving to the right. So when these two blocks moving to the right, we know that in this region here, the spring element and damping element will be in tension. So when these two elements in tension, so we can draw the free body diagram in compression. All right, but for the area in between block M1 and M2, we don't know what happened in between these two elements here, whether it is in tension or in compression. So don't worry, you can make your own assumption and follow the rule strictly. Follow the rule so that you get the answer correctly. So let's say we assume that x2 moving greater than x1. Okay, if x2 greater than x1, what happened to this area means that block M2 moving faster or more as compared to M1, so this area will be in tension. Okay, so when this area in tension, you can draw free body diagram in compression. Okay, that is the assumption that x2 greater than x1. But if you are not dealing with tension condition, you say that if let's say you make an assumption that x1 greater than x2. If let's say x1 greater than x2, means that this area will be in compression. So when it is in compression, you draw here in tension. Okay, clear? So now, let's put all the forces here inside this FBD. So we have here K1, X1. Okay, we have here C1, X dot 1. Why only one coordinate? Because this area deal with one coordinate only. But this area, you deal with two coordinates, X1 and X2. So since for this FBD, I make an assumption that K2, so I put it something like that. So this is C2, and then I put it something like that. So it is always the greater coordinate minus than the less displacement, the less displacement for the coordinate. So this is X2 minus X1, and then this is X dot 2 minus X dot 1. Okay, so we are not really interested to know about this one. Okay, so I delete back all this one because it is attached to the pitch end. So this is our free body diagram. Right. So remember for this side, if let's say, so let me draw it here. So I use the blue color. So for this side, okay, if let's say you make an assumption that, x1 greater than x2, so you should get something like this one, yeah. So you should get here K1 multiplied by x1 minus x2. This one you get this is K2, C2, x dot 2 minus x dot 1. So you can use the blue color here or the one that I drew it here or sketch it here. You will get the same answer, right? So it is based on your assumption whether S1 greater than S2 or S2 greater than S1. And then your direction of force or the vector of the force must be correct. Okay, so let's use the red color here. Okay, this is our free body diagram. Right? So from free body diagram, we know that this is a linear motion, this is a translational motion. So our Newton's law here, it is basically is equal to, to the right is positive, to the right is positive. So we have summation of forces is equal to MA. That is our Newton's law. So let's derive it one by one. For block M1, so we know that there are 4 forces for block M1, 1, 2, 3, and 4 connected to block M1, and there are 2 forces connected to block M2. So for block M1, we have minus, so let's use the black color, minus K1 X1 minus C1 X dot 1 plus Y minus, because this direction is to the left and we follow the coordinate system to the right is positive, and this one is going to be positive there, so plus, so you have K2 X2 minus X1 plus C2 X dot 2 minus X dot 1. That is equal to mx double dot 1. That is for block M1. Okay, so let's divide this part. So for block M2, so we have minus K2, okay, X2 minus X1 minus C2 X dot 2 minus X dot 1. That is equal to M2, this is M1, yeah? This is M1, this is M2, X double dot 2. Okay, so you have 2 equations. Let's rearrange that one. Let us rearrange this one. Yeah, so let's rearrange. We have one equation as M1 X double dot 1. Okay, plus, so this C1 here, this C1 X dot 1, we can combine it with C2 X dot 1 there. So since negative, negative, so we bring to the other side, you get positive. So you get C1 plus C2. Okay, and then you have X dot 1 minus C2 X dot 2 plus, so the combination part I use the red color. So you have K1 plus K2, and then you have this one as X1, and then you have minus K2 X2, that is equal to 0. So let's make it smaller. That is the equation number 1. Okay, so let's mark it as equation number 1. Okay, and then from the second block, we have M2 X double dot 2. Okay, so we have M2 X double dot 2, and then plus, so you have C2, C2 X, X dot 2 minus X dot 1 plus K2 X2 minus X1. That is equal to 0. This is equation number 2. Okay, so we get 2 equations representing block M1 and M2 representing the system. So this is what we call it as, equation of motion. If you have a question with value M1, M2, C1, C2, K1, K2, you just substitute all the value, you get a nice equation in terms of numbers. Okay, that is equation of motion. Let's represent this equation in terms of matrix. Okay, so let's make it as black color, right? So the first matrix basically representing double dot 1, double dot 2. Okay, and then the second matrix is basically representing dot 1, dot 2. And the third matrix is basically representing, okay, X1, X2. Okay, that is equal to 0. So if we represent this equation of motion in matrix form, you should get the same representation but different form. A different form. Okay, so let's look at the first equation, equation number 1 here. Yeah, so for X double dot 1, you get M1. So let's use the blue color. So you get M1, but you don't have the X double dot 2 for the first equation, which is X double dot 2 is equal to 0. And then for X dot 1, you get C1 plus C2. And then for X dot 2, you get minus C2. When you multiply back, you get the same equation. Okay, when you multiply this one back, you get the same equation as the equation 1. Okay, and for the X1 for K, so you get K1 plus K2. And then this is minus K2. Okay, that is for the first equation. For the second equation, you don't have any terms for x double dot 1. So this is 0. And this is m2. And then for x dot 1, you get minus c2 because this is minus here. And then for x dot you get c2. Okay, and then for x1 you get minus k2, and then for x2 you get k2. So this is our matrix representation for the same equation of motion. And normally in the books, in our books, normally this one and this one and this one, they call it as mass matrix, they call it as damping matrix, and they call this one as stiffness matrix. So this is our third objective, yeah. So to define mass matrix, damping matrix, and K matrix. Later on in chapter 5 for Dunkley's and Rayleigh, we will use this one, yeah. Okay, and we will use this one also for a shortcut in our derivation for natural frequency and motion. Okay, so up until now, do you have any question? Let's see. Up until now, do you have any question? Okay, yeah? Alright, good. Okay, kalau okay, no problem. So, cantik. Okay, so saya pergi perlahan-lahan sikit. Alright, so kalau tak ada question. Okay, so let's go back. Okay, so now, we know that in order for us to get the objective number 4, objective number 3, which is natural frequency and motion. We know that for any systems, in our case, we make an assumption. We make an assumption that the response is basically in terms of, I use the same symbol as rho, because rho is our reference book. So this small xt is the response, this one is the response, and this one is the amplitude. We call it amplitude. I use the capital X. So this is x1 sine omega t. Okay, forget about the phase angle here because phase does not reflect the amplitude of the response. It's just a phase in between one waveform to the other waveform. Okay, so forget about phase first. Phase later on we will represent it in our final equation. For derivation, we forget about phase first because it makes our calculation much easier. Otherwise, we have to use the trigonometry as what represented in Ross book. Okay, and then we can make an assumption that this is similar as chapter 2 and chapter 3. So we can make assumption that our second response from the second block is basically equal to amplitude, the second amplitude sine omega t. And of course, the omega is similar because it is the same systems. You have the same omega, but the amplitude for block M1 and M2 is basically different. So it can be represented as x1 and x2. That is our assumption for our response. Okay. And if we differentiate this twice, if we differentiate this one twice, we get x double dot 1 and then x double dot 2. I think you know on how to differentiate this one, yeah. And then let's name this one as A, and then sub A into 1 and 2. So subs A into 1 and 2. Okay, so when we substitute A into equation 1 here, into x double dot 1, x double dot 2, x1, x2, and x dot 1 and x dot 2, you will get a new representation. Okay, so in order for us to derive the equation, the natural frequency and motion, we are not really interested to know about the damping matrix here. Okay, because we know that damping will not contribute to the natural frequency. Okay, so our natural frequency omega n is basically depending on the K and the M. It depends on the stiffness matrix and it depends on the mass matrix. So for deriving the natural frequency and mode shape, which is every natural frequency, you will have mode of the system. So for example, 20 hertz. So if let's say the system vibrate at 20 hertz, so you have one mode for that 20 hertz. And if you have another natural frequency, 30 hertz, you have another mode that representing the system vibrating at 30 hertz. Okay, so you have two different modes. For 2D governance system, you will have two natural frequency, you will have two modes. So in this case, we are not really interested to know about the damping or the damp system. The undamped system is more than enough for us to derive the natural frequency and motion. Hopefully you clear that one, yeah? So if let's say in the question, in the exam question, you have the damping part for question A and B, but question C asks you to determine the natural frequency and mode shape, you can write something like this. So you can write that the C matrix is equal to 0. Okay, the C matrix is equal to 0, or we neglect the C matrix. So we will left with two matrices. We will left with the M and with the K. So let's write back the equation as M and K. Yeah. So we have M1 x double dot 1 plus, okay, so forget about the C. So plus, so you have K1 K2 x1 minus K2 x2. Yeah. So we have plus, we have K1 plus K2 x1 minus K2 x2. That is equal to 0. When we forget about the C elements, we get this one. And from the second equation, we have M2 x double dot 2. So we have M2 x double dot 2 plus second terms we have K2. So we have K2 x2 minus x1. That is equal to 0. And substituting equation A into equation 1 and 2, we should get this one. I use the different color. So we should get this one. So we should get M1 multiplied by, if you differentiate this twice, you will get minus x1 omega squared sine omega t. Okay, if you differentiate this one, if you differentiate this one twice, you get minus x2 omega squared sine omega t. So let's substitute it here. So you get minus x1 omega squared sine omega t, okay, plus k1 plus k2 multiplied by, so let's see if you have an equation here. Admit, okay, so plus k2, so substitute x1 here, so you get x1 sine omega t, okay, x1 sine omega t there, and then minus, you get k2 x2 sine omega t. That is equal to 0. Okay, and substituting the same expression into equation 2 there, so you get m2 minus x2 omega square sine omega t, okay, plus k2, so you get here x2 sine omega t minus x1 sine omega t. That is the whole expression. And we can see from the blue equation here, we have the same terms, sine omega t. So let's factorize it out, outside. Okay, let's factorize it outside. You get m1. Okay, sorry. You get x1, so you get k1 and k2. So let's arrange it accordingly. K1 plus k2 minus m1 x1 omega square. This is equal to, this is x1, sorry, this is so this is x1 minus, okay, so you get m1 x1 omega square, so this is sine omega t is equal to 0, so this one here, then this one is equal to k2 minus m2, okay, omega square. All right, so this is let's put x1 straight away inside there. So you get k2 x2, this is x2, so factorize the sine omega t is equal to 0. Okay, so you get this expression, and we know that sine omega t will not be equal to 0. Otherwise, the whole equation will be equal to 0. So there's no vibration, no point we derived it. So sine omega t will not be equal to 0. So what are the terms is equal to 0 in order to satisfy this equation? So in this case, our equation here, so we get, let's arrange it this way. K1 plus K2 minus M1 omega square. All right. Okay. This is x1, that puts the x1 outside, is equal to 0. Okay. Oops. Okay, so you have x2 over there. Okay, I forgot that one. Yeah. So forgot this one. Yeah. Sorry, my mistakes there. I did a mistake here. So let's delete it again. So let's delete this one again. Okay, so you have x2, two terms here. You have x2. Okay. Okay, so let's delete this one. So you have, so this is k1 plus k2 x1. So this is x1. So you have sine omega t. And then you have the other one, which is minus k2 x2. So sine omega t. So let's put the sine terms outside. Yeah? Let's put the sine term outside the bracket. Okay. Alright, so minus. So minus k2 x2. And then we put everything as sine omega t is equal to 0. And then here you have the minus k2 x1 and everything sine omega t is equal to 0. Okay, so we know that sine omega t is not equal to 0, so the term inside the bracket will be equal to 0. So in this case, we will have, let's write it in matrix representation, k1 plus k2, okay, bracket minus m1 omega square. So the whole thing will bracket it, that is x1 minus k2 x2 is equal to 0. And then we arrange everything back, k2 minus m2 omega square. So the whole things we multiply by x2 and then minus k2 x1. Okay, so this is like that one. So that is equal to 0. Okay, so this is the new arrangement of our equation. That is the new arrangement. So let's call this one as, let's say, C equation. Okay, so that is the new arrangement using the estimated response. Yeah. All right. So now let's arrange this one in matrix representation. So you should get in matrix representation, you should get so we will get like this big matrix, x1 and x2. So you get as 0 and 0 there. So from the first equation up here, from the first equation, we know that the terms multiplied by x1 is equal to k1 plus k2. This is plus minus m1 omega square. And the term multiplied by x2 is minus k2. So we put minus k2 over here. The second equation, the term multiplied by x1 minus k2 is always reciprocating. Yeah? Here and here always reciprocating. Okay, Maxwell reciprocating theorems. All right, so this one, the second one, you get k2 minus m2 omega square. That is our matrix representation for equation C. All right. So in order for this equation to satisfy all values of x1 and x2, the determinant of this matrix must be equal to 0. I think you learned this before in mathematics subject. In order for us to satisfy all values of x1 and x2, our matrix here, the big matrix here, the determinant of this matrix will be equal to 0. Okay, so what we can do here is basically we can set determinant of k1 plus k2 minus m1 omega square minus k2 minus k2. So this is k2 minus m2 omega square will be equal to 0 to satisfy all values of x1 and x2. All right. So in order for us to solve this one further, let's make an assumption. In the real exam or in the real case, you will have the real value of k1, k2, m1, and m2. So when you substitute the value, you get the value, and it's easy for you. You get the numbers, and it's easy for you to solve this one mathematically. Yeah. But in this case, I represent it as unknown parameter k1, k2, m1, m2. So let us make another assumption. So let's k1 is equal to k2 is equal to k, and m1 is equal to m2 is equal to m. Let's use one particular representation. So our equation is now here, we will have do 2k minus m omega square. That is minus k. This one is minus k. This one is k minus m omega square. So you get is equal to 0. So let's solve this one. Let's solve this one. So you know that you get 2k minus m omega square multiplied by k minus m omega square for determinant, yeah? Minus k multiplied by minus k, that is equal to 0. Okay, so when you solve it further, you get, let's write everything first, yeah? So 2k square minus k m omega square minus 2k m omega square plus m square omega to the power of 4 minus k to the power of 2, that is equal to 0. Rearrange this one, you get m to the power of 2 and then omega to the power of 4. So you get minus 3k m omega square, so plus k square, that is equal to 0. So this is the unknown, that's why it looks like a bit difficult to solve it, but in the real exam you get numbers, so it's easy for you to solve this one. So look at this question carefully. You have to the power of 4, you have to the power of 2, you have to the power of 0. So this is fourth order. So when you have fourth order equation, you can reduce it to second order. So how to reduce it to second order to quadratic equation? We use one particular representation. So let lambda is, I use the same symbol as now, is equal to omega square. Okay, so we represent it as one particular, or we reduce the order. So we have the equation here as m square lambda square minus 3k m lambda plus k, there is no omega, so you maintain k square as is equal to 0. Okay, now this equation we call it as characteristic equation, and these two equation we call it as characteristic equation. Okay, how to solve this one? Okay, how to solve this one? If you have the real value m, you get numbers, 3km you get numbers, k you get numbers, and it's easy for you to use the calculator by using quadratic equation to get the roots of the equation, roots 1 and roots 2. So, but if you have the unknown parameter like this, so you can determine the lambda 1 and lambda 2 using the mathematical expression. So you get minus b plus minus. So you get this one, b square minus 4ac. Sorry, I think I write it correctly. If not, then you have to correct me. Divide by 2a. Okay, so what is a in this case? What is a? So this is a, this is b, and this is c. Substituting everything into the equation, you should get lambda 1 and lambda 2. You get 2 lambda. Okay, so what is lambda here? So we use this equation back. We use this equation. So in order for us to determine the omega n, so you should have omega 1 and then you should have omega 2. So what is omega 1? That is equal to square root of lambda 1. And what is omega 2? Square root of lambda 2. Be careful when you write this expression. Lambda 1 is always the smaller value. Okay, lambda 2 is basically the bigger value. So this is the bigger value. Okay, that is the bigger value. So if you have, let's say, 2 lambda, one is 4, another one is 8. So use omega 1 from 4 value, use omega 2 from the 8 value. So always the smaller one, because our frequency, we arranged it from smaller to the higher value. So now we have the natural frequency. Okay, then we want to determine the mode shape of the system. So in order for us to determine the mode shape, we need to know the amplitude ratio. So we can represent our amplitude ratio R as x2 divided by x1. Okay, we can represent it as x2 divided by x1. And how we going to get this value? So if you look at the equation, where I write it, okay, this equation, equation C, from equation C, we have the expression of x1 and x2. Let's rearrange it, okay, from the first equation, from equation C. So from equation C, we have, you should have, okay, let's write it back. So let's take this one. Let's take this one. So I take this one. Okay. So copy Okay, so let's paste it here. Senang, easy for us to discuss. So let's paste it here. So paste it here. Okay, from these two equation, okay, we know that in order for us to get, to get x1 x2 divided by x1, you can get x2 divided by x1 here. Okay, how to get that one? You bring this term to the other side, you get positive value. So for this one, for the first one, x2 divided by x1, you should get, so let's substitute k as k1 and k2 as k and 1 as m. So you should get 2k minus m1 divided by, this is omega square, divided by k2. From here, okay, x2 divided by x1, so you should get k. So this is not k2, this is k. So k divided by, so k minus m omega square. So again, this is not m1, this is m. We substitute everything as our assumption value. As our assumption value. So this is m. All right, so that is the ratio. So we can write our ratio here as 2k minus m omega square divided by k, or we can write it as k divided by k minus m omega square. Either one. In the exam, you don't have to use these two equations. You just need to select one of it. So you can use either the first one, or you can use either the second one. All right. Okay. So that is the ratio. You need to know this ratio. You need to know this ratio. Okay. So now we can represent two mode shape. So we can represent our R1 here as, okay, so x2 and x1. Okay, as x2 and x1. Okay, and normally I put it as this one. Okay, what is this number 1 here? That is due to the first mode, due to the first natural frequency. So mode shape, the first mode shape, due to the first natural frequency. Later on, we will write it as this one. That is the second one. So we have x2 and x1. Okay, so we divide this one. We divide x2, divide x1. So we divide this one. Due to the, so let's put it outside. So that is due to the second mode. So this one, let's put it outside. So this one due to the first natural frequency. So what you should get here, if you use the first one, we use the first one, 2k minus m omega square. So we should get here 2k minus m. This is omega 1 square because we use the first mode, the first natural frequency. So divide by k. That is the ratio. And this one, you should get 2k minus m omega 2 here. That is due to the second natural frequency. Okay, so that in the real exam, you get the real value here. So you get a numbers, maybe 0.7, maybe 1.3, maybe minus, and so on. So you get the amplitude ratio here as the real number, R1 and R2. Okay, so that is the ratio. In terms of value. Then, once you get this one, we can represent our mode shape vector. So So normally, it will be marked as this one. So let's okay, so this is the mode shape vector due to the first natural frequency. The mode shape vector due to the first natural frequency. So it will be representing as this one. Okay, so you have x1 due to the first natural frequency, and you have x2 due to the first natural frequency. Okay, and we can write this one as x1 due to the first natural frequency, and then x2 here from R1, you can bring this x1 to the other side. So x2 is equal to R1 x1 1. That is representation of the first mode shape. And for the second mode shape, we can use this one. we can use this one. So x1 due to the second mode, due to the second natural frequency, and you get x2 due to the second natural frequency. Or we can represent it as x1 due to the second natural frequency, and then R2 x1 due to the second natural frequency. Okay, so if you can see here, all the representation is basically in the form of x1. Okay, with the amplitude ratio value R1 and R2. So it's easy for us to get the solution later on. Okay, that is the mode shape. So that is our objective number 3. So we get the equation of motion, we get the matrix representation, we get the natural frequency, and then we get the mode shape. Now is the response of the equation. So how to represent the response? So in order for us to represent the response, so normally I will put it this way. So response is a small x. Normally I use it as t, and then the second one as x2 in the form of xt. Okay, so in order to write this one, so we can write it differently, something like this one. So x1 due to the first natural frequency, that is due to the first natural frequency, and then x2 due to the first natural frequency. Okay, so if we write this one, we know that from the mode shape here, we can write it as this one. So x1, okay, due to the first natural frequency, and we know that our response is in the form of sine omega 1t plus, now I put the phase angle there. Okay, for the response we have the phase angle phi1, right? And then the second one we have from that expression, so r1 x1 sine omega 1t, that is due to the first natural frequency, plus p. Okay, I use P1 in the expression. So I use P1 in the expression. Okay. All right. And then the second part we can represent as 1 T response in the due to the second natural frequency, and x2 T response due to the second natural frequency. Okay. That is equal to our mode shape here. So you have x1 due to the second natural frequency sine omega 2t plus p2. Then you have r2 x1 due to the second natural frequency sine omega 2t plus p2. That is our response for every mode. This is mode 1. This is mode 2. Okay, so if we want to know the total response for S1, so total response for both block M. Okay, so X1 total is basically is equal to X1T due to the first mode or due to the first natural frequency plus X1 X1T due to the second natural frequency. And we should know that the second total is equal to X2T due to the first one plus X2T due to the second one. Okay, so means that we can add up this one. We can add up this one X1 and X1. So you should plus this one, and then this one and this one, you should plus this one. In order for us to get, okay, so let's use the green color. So you get this one, and then this one, you get the second one. Okay, so that is the total response of the system. Okay, guys, until now, do you have any question? Setakat ni okey lagi. Matrix form boleh jadi in terms of theta juga ke depend on coordinate. So for derivation of natural frequency, mode shapes, and so on, and the equation of motion, I don't use the theta first because theta is basically just a phase angle. But in the response, I include the theta in our solution. So in the response, I put the theta in as our solution. So we have 4 unknown here. If you look at this equation, we have 4 unknown. We have x1 due to the 1, and then you have x1 due to the second. Okay, right? And then you have P1, and then you have P2. So how to get this one? It's from the initial condition. So you have 4 unknown, you have 4 equation later on, you have 4 equation. Okay, you have 4 equations, so you can solve it simultaneously to get x1, x2, x11, x12, p1 and p2. When you substitute it into the equation, you get the response of the systems. Okay, so hopefully that answer your question, yeah. Okay, so Dania Ayub, so matrix form boleh jadi in terms of a theta juga ke depend on coordinate. So matrix form is depend on the equation of motion. So daripada equation of motion, you represent it in matrix representation. Okay. Alright. So now, last part for today. So there is another way. There is another way to do this one. This is a bit longer representation or longer expression, but we have a short expression from this one. From this one here. From here. Okay. Okay. What is our equation? Okay. From here. From matrix representation, we know the mass matrix, we know the C matrix, we know the K matrix straight away. All right. So from here, in the exam, you don't have to do all this one, all this derivation, but you can simplify it a bit. We know that the determinant of matrix K minus matrix M multiplied by omega square must be equal to 0. So you can use, let's box this one. You can use this equation. So this is the shorter way to do it. You can use this equation in order for us to determine the natural frequency and mode shape. Okay, so let's use the same example here. So let's say you get this one. So you get determinant. So what is our K matrix? What is our K matrix? So K matrix here. What is our K matrix? So forget about the damping, yeah. So we get this K matrix. What is our K matrix? So this is the K matrix. Okay, so let's copy this one. Okay, so this is our K matrix. Okay, so copy this one. And then M matrix is very straightforward. All right, so let's put it here. All right. Okay. Okay, so let's put it here. Yes. Okay. So we know that our matrix here so let's paste it here. Okay. So that is our K matrix minus, okay, so let's use the blue color, minus the M matrix. So earlier we have M1, 0, 0, M2 multiplied by omega square. So since this is determinant, so we should use a straight line there. Then this is equal to 0. Okay, substitute the assumption that we used before this. So you have 2K minus K minus K, okay, minus M0, 0 multiplied by omega square. That is your matrix now. So this is very straightforward to solve this one. So these first terms you solve with the first term, second terms you solve with the second terms, third term you solve with the third terms, and fourth term you solve with the fourth term. So what you should get here, you should get the determinant of 2K minus M multiplied by omega square. So you get 2K minus M multiplied by omega square. And then you get minus K. This one is minus K minus 0. 0 multiplied by 0. So you get minus K there. And then minus K minus 0, you get minus K there. And then K minus M omega square. So you get K minus M omega square. So this one. So let's copy back. Let's copy back this one, yeah. So let's copy. Copy. It's that one. Undo. Let's undo this one. So let's copy. Okay, let's copy this one, yeah. So this one, the one that we did it before. Okay, so copy this one. So I use the same color, so not a bit confusing. Okay, so let's paste it here. So paste it here. You can see that these two is a bit similar. Okay, you can see that it's similar, but we reduce a bit on the step by using our equation here in the red box here. You use this equation, use the matrix representation, and straight away you get this representation. Okay, and then after this you follow the same steps, do the determinants, and then represent omega to the power of 4 as omega to the power of 2 with lambda, and then so on, then substitute and get the omega n, get the response. It's similar step, but for at the beginning you reduce a bit step, especially to substitute x1 sine omega t, x2 sine omega t, and so on into the equation. And by using the expression here, you get the same matrix. But in the exam, if you use this one, if you use this particular equation, you don't know which one is the x1 and which one is the x2. You get this one straight away. You get this expression straight away. But you should know that this one is basically multiplied by x1, and this one here is basically multiplied by x2. So from here, you know that r is equal to x2 divided by x1. So you should know from this method, you know on how to get the ratio in between x2 and x1. Okay, so from here, we know that this one, if we can visualize it, we know this one, it is basically multiplied by x1, and then this one is basically multiplied by x2. So you rearrange x2 divided by x1, you get the same expression as before. So you get 2k minus m omega squared divided by k, or using the second equation, you get k divided by k minus m omega squared. So once you get r, then it's easy for you to calculate the mode shape, and easy for you to represent the response in the equation. Okay, guys, I think that's all for today. Until the response, and then after this, I will prepare a video with the exam question with the real value and how we go from step 1 until the final step for the response. Okay. All right. So in the next session, we will discuss the bouncing and pitching cases. Bouncing and pitching case. Okay, guys. All right. So any other question until now? Don't forget to write your full name. Don't forget to write your full name. Don't forget to write your full name. So let me take the attendance form. Okay. Right. Any other question, guys? Okay. If you have no more question, so again, please look at the UFuture continuously, and also the YouTube, especially in UFuture in the group content and also the learning activities. I'm monitoring your progress over there, and then every week you have to, since this is last month, so every week you have to go through the information in UFuture. And then we will discuss further later on. Especially if you have a question, you can post it in the UFuture, or you can WhatsApp me. Okay, so if you have no question, that's all for today. Thank you very much. See you again. Bye-bye now.